lectures for Class 5. We'll be covering lists and recursion in Prolog, which corresponds to the material in our Prolog text in chapters 3 and 4. Recursion is central to a declarative language like Prolog, which contrasts with iterative languages like Pascal or even Java, where much of the repetitive work is done through iteration. So let's jump in and see how lists work. Well, not surprisingly, lists have a recursive definition. So the base case is the empty list. That's a list, and it's represented as left angle bracket, right angle bracket, or square bracket with nothing in it. The non-empty list is represented by, well, it'll have to have at least one element, which we'll call the head, and then there's a vertical bar there which separates the head from the tail, and the tail is a list. So the head is going to be typically an atom. It's some element, could be a list, but for now let's just think of it as an atom. The separator, which shows the difference between the head and the tail, which is always a list. Now, the tail could be the empty list because that's a list, or it could be some other list. So, for example, here is a list in normal notation of one item. Now, we could rewrite that using our head and tail notation. So we know that the first element of the list is the atom A. Then we have the list, the separator between the head and the tail. And because A is the only element in our list, it's a list of length 1, we know that the tail is the empty list. Likewise, let's take a look at the list of 2 items. Here, for example, the atom A followed by the atom B. And we could also write that as using this recursive head and tail notation, where the first element of the list is, in fact, the atom A, and the tail is another list whose head is B and whose tail is the empty list. Let's put our new knowledge of lists and Prolog to work by trying to write some recursive definitions that give us information about lists. And the first predicate we're going to work on, we'll find the last element in a list. And I'm going to call it my last because there's already a built-in predicate called last, so we're going to rewrite it from scratch. So what's the base case? Well, the base case, if we think about it, can't be the empty list, because if a list is empty, there is no last element, so it ought to fail. So the base case, in fact, is going to be a case where the list has exactly one element, like we saw in the previous video. Now, if there is only one element in the list, well, we know exactly what element we want to return, and it's going to be that element. So the base case is pretty easy. What about the recursive case? What if there's more than one element in the list? Well, if we've gone past the base case, that didn't match, we know that the first element, we know that there's more than one element in the list. And if there's more than one element in the list, we know that the head cannot be the last element. So we don't care what it is, and I'm going to put the name of a variable there, underbar, and underbar is a name of a variable, but it doesn't bind to anything. It's basically an anonymous variable. It says we don't need to spend the work figuring out what that is because we're not going to be using it. So we don't care about the head, but we do care about the tail, because we know that this tail, which I'll call L for list, contains the last element that we're looking for. Now, we want to return that last element, and the question is, how do we find it? Well, here's the cool part about recursion. We know that the X we're looking for is the last element in L. Do we happen to have a predicate that returns the last element in L? Any list? You bet we do. It's called my last. So let's write my last. We'll put L as the argument, which is the same as the list for the predicate on the left-hand side, except we've stripped off the first element, and we'll return the last element of the list L. So that's the definition, and let's try it out and see if it works. So we'll load the file I've called class 5, and let's see. Now I said that last of the empty list should return false, so let's see if that's really true. So we'll give it the empty list as our list, and we'll ask for the last element and see what happens. False. Okay, so far so good. Let's see if the base case is working. So let's search. Let's see if we'll have an element called spike as our only element, and let's see what that is. Can we find the last element in that list? Hey, by golly, we can. Are there any other last elements? Nope. There's just one last element, which is exactly the behavior we wanted. Let's take a look and see how the recursive process works in looking at finding the last element of a list of 3 elements. So we'll have a list of A, B, and C, and we'll want to find out what the last element of that list will be. So the first thing we'll do is call myLast. That makes sense. And we can see the list as the first argument, and the last element is this funny looking variable with an underbar G346, and that's basically Prolog's internal name for our X. And it's not instantiated yet because we haven't bound it to the last element of the list, and that can only happen in the base case. So it's just going to stay there as an unbound variable until we bind it in the base case. So the first thing we'll do is call myLast, and what's going to happen is we'll be able to match that second predicate, which will strip off the head of the list and look for myLast or the tail, and that's exactly what happened. So instead of looking for myLast of ABC, now we're just having to look for the last element of BC, which is an easier thing to do. And what do we expect next? Well, we'll look for myLast of the list C, and now we have a list of one element, and you and I know, because we wrote the predicates ourselves, that that's going to match the base case. And sure enough, it matches myLast of an element, a list of one element, and now it's bound that dummy variable to C because it was the base case. Well, now that we know what the last element of the list containing C is, we know what the last element of the list BC is, and thus we know what the last element of list ABC is, and sure enough, we'll return X equals C. Let's try writing another definition Prolog for a predicate that operates on lists, and that's the predicate to see if something is a member of a list. So let's say we're trying to find out if whatever we bind X to is a member of some list. Well, the easiest case we have is that the head of the list happens to be exactly the element we're looking for. Now think for a minute. If we've succeeded and found X as the head of the list, do we care what's in the tail of the list? Not at all, because we've already found that it's a member. So I'll put an anonymous variable there for the tail, which means we don't really care. And that's our definition. That'll succeed, and so it'll say that X, whatever that is in fact a member of the list. Now the next case is going to be the recursive case, and it's going to be the case in which X is not the first element of the list. Now, if X isn't the first element of the list, it's either going to be in the tail of the list or it's not going to be there at all. So if it's not the first element of the list, then we don't care what it is, and we'll put a anonymous variable there. And we're hoping that it's in the tail of the list, which I will call L. Now, Let's think. We want this predicate to return true if X is a member of that list which had something which wasn't X and the tail is L. Well, it should return true if X is contained in L. How do we check that? Well, we can check it recursively. Member X L. And a recursion will work because our L will be one item shorter than the list we started with, and we'll keep going down until either the head of the list is an X, in which case we succeed, or L eventually becomes the empty list, and that's not going to match either predicate, and it'll return false, which is exactly the behavior we want. So let's see if it actually works. Let's reconsult class 5, and which I had on trace, which we will abandon. Let's try again. Okay, so class 5. Okay, this time. All right, so let's see if something is a member of the empty list first. So we'll see if Fluffy is a member of the empty list, and I'm hoping it says false. Ah, what do you know? Okay, so now let's see if Fluffy is a member of some list that has Fluffy in it. Now, what if Fluffy is the only element in the list? Well, we know it's going to match our first or base case predicate because this list is a list where Fluffy is the head and the tail is the empty list. Does it work? Yes, it does. How about this? What if Fluffy isn't the head of the list? And we've got the head of the list is Spike, and Shep, and we'll put Fluffy in third, and we'll put Tweety in as another element of the list. And let's see if it comes out true. Sure it does. Let's watch Prolog trace this. So we'll say trace, so we can see this recursion. Okay, so we'll call the original predicate. Well, it didn't match, Fluffy didn't match the head of that list because the head of that list was Spike. So it strips one element off in a sense, and we apply member to the tail of the list, which is Shep, Fluffy, Tweety. And then Shep isn't that element either, so now we see if Fluffy is a member of the list Fluffy, Tweety. Sure enough, it is. And so we can recurse back out, and we know that the member function is going to be true. Here's a third Prolog predicate dealing with lists, and this will be the Prolog predicate count. And the idea is to count how many elements there are in the list. Now in this case, we can figure out what the base case is pretty easily, because if the list is empty, we know that there are 0 elements in the list. Okay, what about a list with more than one element in it? Well, if there's more than one element in it, we don't really care about what the element is, the head of it, so we'll give it an anonymous variable to match, and we'll call the tail L. Now we don't know how many elements there are in that list where the underlined underbar variable is the head and L is the tail, so we'll call it something N. But we do know that the number of elements in this list, which has the underbar for the head and the L for the tail, is 1 plus the number of elements in L, because we've got this head, that's 1, plus the number of elements in L. So what we're going to do is count the number of elements in L, which I will call M, that count, all right? And then we'll add 1 to N. So we'll say N is, and I'll explain why we're saying is in a minute, M plus 1. Now, why didn't I say equals? Well, because equals is an evaluation predicate that returns true or false if they're equal or not. And is actually does the arithmetic. So if m is 10, n will be bound to the value 11 instead of some expression like m plus 1, which isn't what we want. Okay, so that's our set of predicates for count. Let's see if it works. I've turned trace off this time, and we'll reconsult class 5. And let's try it. Okay, so the base case was the empty list. So what is the value of the empty list? And we'll just call it x, because we don't know what it is yet. And sure enough, x is 0. What about counting a list of one element? We'll put maybe Shep will be our one element. How many elements in that list of one element? 1. Okay, well, let's give it a slightly longer list to count, and I'll just copy this list here. How many elements in that list? We'll call it I, just to make things more interesting. And I equals 4, which is exactly what we'd expect because there are 1, 2, 3, 4 elements in the list. And if you want, you can try running that under trace, and you can see how it basically, for each recursive case, uses a list that's one item smaller until it reaches the base case, and then it recursively goes back up, adding 1 to n each time. Next, we're going to look at a classic bit of Prolog, which is the predicate append. Now, there's a built-in predicate append in SWI Prolog, so we're going to write a predicate called myAppend. And here's the idea. So basically, the idea is that we're going to have two lists, and we want so we'll have two arguments in our predicate, and then we're going to try to bind the third argument to the result of combining those two lists into a single list. So the insight that underlies append is that if the first argument is the empty list, then we know that the result of appending the first list and the second list, whatever the second list is, must be the second list. Pretty straightforward, huh? Okay, so let's try writing the recursive case. Well, if the first list isn't empty, then we know it has a head and a tail. Right? Now, in the next to last iteration, recursive call, that tail is going to be the empty list, and it'll call our base case. But for now, it doesn't really matter what the tail is. All right. And then there's some other list, which we'll call list 2. And there's a list 3, the third argument, which is the one we're combining. Now, let's think about it. What is the first element of that combined list going to be? Well, because we're putting the first list first and the second list second, the first element of the combined list has to be the first element of the first list, which we know is H. Okay, so what is the rest of that combined list going to be? Well, that combined list is going to have all the elements in T, the tail of that first list, coming before all the elements in L2, right? So we'll call that L3. So L3 is going to contain all the elements of T followed by all the elements of L2. How are we going to do that? Well, we'll do it recursively. So how do we get all the elements of T, follow a list that contains all the elements of T followed by all the elements of L2? Well, we'll append together T, L2, and we'll call that L3, which is exactly what we want. And that's the definition of append. So let's try running that in our Prolog. So I'll reconsult class 5. Now, what happens if I try appending the empty list to the empty list? So we'll call this last thing L. Well, by golly, it's the empty list, which is exactly what we expected, because we matched the base case. We matched the base case, which was the empty list, and we returned the second list, which happened in this case to be the empty list. So that's exactly the behavior we expected. What about appending a list of one item? Well, let's see. We'll try first. We'll append the empty list to a list of a whole bunch of items, which I happen to have around, and we should be able to get out exactly that second list. All right. And now, what about where that first list isn't empty? So maybe this first list contains some element called Rex, and our second list is going to be our animal friends, and our third list will be L, and sure enough, that gets appended on. And so just as a to make things complete, let's append a long list of 4 items to another list of 4 items, and we should get out the list of 8 items, and that's exactly what we get. So if you can understand append, you'll really have understood how recursion and Prolog works. Try putting together yourself. You might try, if you're having trouble with it, you might try turning on trace and watching